Hello, welcome to yet another graduate classical mechanics video from Dr. Viv. Today we'll be studying the fascinating topic of motion of a heavy top. Now you may have played with finger tops like this. The motion we're considering is a little more restrictive than the finger top because the finger top, as you can see, drifts and moves around. We would like to keep the point of contact fixed. So a more appropriate demonstration for what I'm about to present would be a gyroscope. A gyroscope such as this one. I make it go by pulling a thread that I have wound around the gyroscope. And just to make sure that the gyroscope stays with one point fixed, I have this 9-volt battery terminal. So you notice that it's spinning really fast. And as soon as it acquires some sort of an angle, it starts doing this other motion, which is called precession. And as the top slows down due to viscosity of the air and all the vibrations and jitters in the system, you notice the precessional rate actually increases. Now, this precession we are observing is what's called the slow precession. There's also a fast precession, which is more directly related to how fast it's rotating. So we'll be studying these concepts in today's video. So brace yourself. It's a fairly technical subject because the proper way to describe a top consists of introducing what are called Euler angles. So Euler angles we'll introduce in 3 stages. These are considered the appropriate angles to use to study any rigid motion, rigid body motion. And because we need one point to be fixed, we'll make sure the non-inertial and the inertial coordinate systems share the origin. So the first step in creating the Euler angles would be to draw or sketch the inertial frame. Remember, inertial frames occur with prime, and non-inertial frames occur without prime. So Z prime, X prime, Y prime. Just make sure it's a right-handed frame. X cross Y is Z. So now we have to introduce a series of rotations to introduce the Euler angles. So the first rotation is going to be a rotation about the Z-axis by an angle phi. The Z prime axis stays fixed because you're rotating about it. So to indicate that I'm rotating about the Z-axis, I'll draw a little disk here. So the second Z-axis, which I will call Z prime, or Z double prime, will be the same as Z prime. Now, because the rotation is counterclockwise, as all rotations tend to be in physics, we're going to have the X prime move to this line, which I'll call X double prime, and that angle is phi. And the Y prime moves in that direction to a new place, which I'll call Y double prime. Now, even though X double prime and Y double prime don't look perpendicular in this figure, you're supposed to imagine that they still are perpendicular. So I'm not ruining the perpendicularity relationship it's all drawn in perspective. For example, x prime and y prime also don't look perpendicular, but you should imagine x prime as coming out of the paper. So in that sense, it's all consistent. So that's the first rotation. And this rotation can be described in the form of a matrix because I'm rotating about the z-axis. The z-coordinate remains invariant. So I can write this as cosine phi, sine phi, 0, negative sine phi, cosine phi, 0, 0, 0, 1. That describes the z-axis being fixed. So I'll indicate the axis that's invariant here. So what this does is it takes the coordinate system x prime, y prime, z prime to the coordinate system x double prime, y double prime, and z double prime, which is in fact equal to z prime. No change. Then we're going to follow this by a second rotation. For the second rotation, I want to rotate about the x double prime axis. So when I rotate about the x double prime axis, if you imagine this as a plate, the plate gets rotated like that. So I'm going to draw a separate diagram so you can appreciate the process better. The original disk I will now draw as a ghost disk. It's still there, but I'm not that fixated on it anymore. That's x double prime. And I made x double prime purposely a little bit longer because this is an important axis. In fact, I'll double draw it. This is called the line of nodes. Okay, so let me draw also the y double prime that I have there. So far I've done nothing, just reproduced what I have there except with the ghost disk. That's my angle phi. Now the next angle is going to be theta, and that's going to be this rotation about the x double prime axis. So here I'm going to draw you should try drawing it with me. It's really an interesting exercise in perspective. So now I have tilted it by an angle theta. So the angle theta would be with respect to the new the x double prime axis doesn't change, but now the y double prime axis has changed. So it's been shifted out of the plane of the paper. So that is now your y double prime becomes y triple prime. And then the z, which was formerly fixed, also rotates because the plate has been rotated. Z also has to rotate. So these two have to be perpendicular. So I'll take care to do that. So that now becomes z triple prime. And that'll be the final position of the z-axis in the rotating frame. So I'll call that z. Unprimed means non-inertial rotating frame. So this angle here is theta. The second rotation can be described by the following matrix. This time, since the x-axis is unchanged, I don't change that coordinate. And then I have cosine theta, sine theta, 0, negative sine theta, cosine theta. All these are counterclockwise rotations. So in this case, the x double prime axis is the invariant axis. And I've gone from x double prime, y double prime, z prime to x double prime, y triple prime, and z triple prime, which is my target destination for the z-axis. Now I have to take x double prime and y triple prime to their final destinations. Remember, in 3 dimensions, you need 3 independent coordinates. So the third Euler angle comes from the third rotation. The third rotation is the one that you make by, again, around the z-axis, but you rotate it counterclockwise by a new angle. So this I'll indicate on the same figure because there's hardly any change between this figure and the previous ones. So now I'm taking use light blue for this one. I'm taking this y triple prime to its final destination y, and that is my angle psi. If I did that, since z has remained unchanged, my line of nodes has to also shift by the same amount. So the line of nodes shifts also by this angle psi. That angle psi is the last ingredient in the Euler angle formalism. So the third rotation would be r as a function of psi. Since again, this is with respect to the z-axis, I keep the z-coordinate invariant. And since the rotation is counterclockwise, I get cosine, sine, negative sine, and cosine. This here becomes your x-axis. So that leads us to our final stage in setting up the Euler axis, where x double prime, y triple prime, and z go to their target non-inertial frame destinations, x, y, z. The product of these 3 rotations takes you from the inertial frame to the non-inertial frame. So you have some weird moment. This top is carrying x, y, z with it as it rotates around. And the inertial frame is the platform we have provided for the top to rotate. Now, there are 3 angular velocities associated to the Euler angles, and they're kind of obvious. The angular velocity about the z-axis is the rate of change of psi angle. So I will call this angular velocity psi dot, because dot means rate of change. The rate of change of phi is with respect to this axis because the angle phi was defined with keeping that axis fixed. So any change in the phi coordinate is associated with the angular velocity there. And lastly, since I use the line of nodes to rotate the plate from the original orientation to the new orientation by an angle phi, this will give us the direction of theta dot. And I put arrows because theta dot, psi dot, and phi dot are all angular velocities, and velocity is a vector in physics. So now we have to find a decent way to relate these different angular velocities. So one way to do that is to use x, y, and z components of them. So let's try to find the x, y, and z components of each of these. The easiest one is psi, because psi has just got a z component. So let's do the easy one first. So I get psi x dot equal to 0, psi y dot. These are angular velocities in the non-inertial frame S. In the non-inertial frame, how do the angular velocities of the gyroscope or the top look? And since there's no other use for psi, I'll just call psi dot the same as the z component psi z. So that's my psi vector. The next easy one is actually theta, because you notice that theta differs from its original location. The new x-axis is here, and the theta is pointing in this direction, so it's got a positive x component and a negative y component, because observe, the y-axis would be positive in this direction, and theta dot dips in the negative y-axis direction. So I get theta x dot would be equal to theta dot cosine psi, and theta y dot is going to be negative theta dot sine psi. And then the z component of theta is identically 0, because theta does not rise above the xy plane. Lastly, the least easy one is the phi coordinate. You observe that phi has to be decomposed not with respect to the original frame. In the original frame, it's easy, it's all z, but with respect to the non-inertial frame, this new Euler angle frame, x, y, z. So this is exactly analogous to spherical polar coordinates. If you notice, the psi, theta, and phi behave exactly like spherical polar coordinates. So using that analogy, I'm just going to write phi x dot is phi dot. So if you want to get the x component, what you have to do first is you take the sine theta component of it, because that would be cosine theta. You take the sine theta component, which will put you in the xy plane, and then take a further sine to give you the x component. And then we can move on to the y. To get the y, you again take the sine component with respect to theta to bring it to the xy plane. Xy plane is the blue lines. And then you take the cosine of psi, because that's the appropriate angle for the y component. And for the z, just like the polar coordinates, it's just cosine of theta. Well, believe it or not, for the motion of the top, this is the easy part. So we have a lot of interesting dynamics that are going to occur next. So once you've set up these coordinates, which was introduced by Euler, hence they're called Euler angles, we then move on to describing the different angular velocities. Now, the angular velocities in the frames is given by the sum of the components. So the x component of angular velocity is going to be phi dot x plus theta dot x plus psi dot x. Let's assemble the ingredients from here. So I get phi dot sine theta sine psi, and then theta dot x phi dot x is 0. And I'm going to call this for simplicity omega 1 instead of omega x. So omega y would be phi dot y plus theta dot y plus psi dot y. Again, copying from here. And I'll call this omega 2. Lastly, omega z, which is phi dot z plus theta dot z plus psi dot z. Well, theta z dot is 0, and psi z dot is just what I've called psi dot, and that'll be our omega 3. So we have our angular velocities, and now we can actually form the kinetic energy of the heavy top. Now, the analysis of the heavy top will be much more meaningful if a heavy top actually looks like a top we see in daily life. The entire theory of tops is very complicated. It was worked out by a Russian woman mathematician called Sofia Kovalevskaya. Sofia Kovalevskaya was a pioneer in the field of not only top theory, but ordinary differential equations and partial differential equations. Along with Cauchy, she is honored the existence uniqueness theorem of partial differential equations and ordinary differential equations is known as the Cauchy-Kovalevskaya theorem. So one of the great mathematicians of all time. So Sofia Kovalevskaya classified tops into 5 types. We're going to study the easiest of the classifications. This is known as a symmetric top, where 2 of the moments of inertia, I1 and I2, are equal, and the third moment of inertia, the one that you spin it around, is not equal to the other 2. So that's the case we're going to study. That case is known as the case of the symmetric top. Now for simplicity, instead of writing I1 and I2, I'm going to call it A. And I3 will be called C, and that is not equal to A. The special case of I1, I2, and I3 equal to each other, in other words, the special case of A equal to C, is known as a spherical top. Now, don't let the name fool you. Yes, a sphere is a spherical top, but so is a cube. A cube has got I1 and I2 and I3 equal to each other. So spherical tops can be more general than just a sphere. Symmetric tops are exactly like what you saw, the gyroscope or this finger top, allowing the axis to be fixed. So if I try to spin the finger top with one axis fixed, then that would be, create a little cup depression in my hand. That would be similar to what I'm doing now. So let me draw a figure to illustrate the symmetric top. Now I don't care about the intermediate portions of the construction that we did to get the Euler angles. So I'm going to just draw the inertial frame, x prime, y prime, and z prime, and my top itself. I'll draw it as a pear-shaped object. You should imagine this to have some kind of shading. Okay. And then the Euler world, we have our z-axis, which is the axis of symmetry of this top. The so-called line of nodes will be here. Remember, I used a double shafted line for that. And then the true x-axis, we shifted from the line of nodes. So in a sense, you have to draw the line of nodes each time you are trying to set up a Euler problem, because otherwise you cannot specify the angle phi. The angle phi requires you to draw the line of nodes. And then this angle psi is there. And finally, you have this angle, which is your angle theta. So that's really the Euler angles right there. The precessional angular velocity, remember the stop went around like this. So the precessional angular velocity is going to be this angular velocity, which you will notice is none other than phi dot. So phi dot will be the focus of all our attention for the rest of this video. Now, what are we going to do with this setup? Well, first of all, we're going to write the kinetic energy term for the top. That's the hardest part. Once we get over that, we can write the Lagrangian. The kinetic energy term following Einstein's summation notation is just 1/2 II omega I squared, where the summation is from 1 to 3. So that's going to be 1/2 I1 omega 1 squared plus I2 omega 2 squared plus I3 omega 3 squared. Now we have to put omega squareds in, so that means I have to take each of these omegas and square them. So that's going to be quite a bit of algebra coming up next. Now, to make things a little bit easier on ourselves and for writing's sake, I'm going to write sine theta as s theta, cosine theta as c theta, and similarly for the other angles. So let's see what we can do with this. Omega 1 squared. So I have the expressions over there. Let me move it to this side so you can see a little bit better. So it's phi dot sine theta sine psi plus theta dot cosine psi, the whole thing squared. And let me write down similarly the other things so I don't have to look at that again. So omega 2 squared is phi dot sine theta cosine psi minus theta dot sine psi squared. Lastly, omega 3 squared, that one, phi dot cosine theta plus psi dot, the whole thing squared. These are just algebraic expressions, so they should be worked out rather easily. Let's do it by expanding the square. I'm going to get so that's a plus b squared. If you just write the general template for this is a plus b squared is a squared plus 2ab plus b squared is what I'm doing really. So I'll put the angular velocities first. All right, then omega 2 squared because of the minus sign, I'm going to get minus 2ab. The minus sign goes away when you square this term. Now, when you try adding these, you'll notice something really interesting. Many of these terms will either cancel or add. So let's just do it. I should probably not say anything else because there's a little more complicated than what I said. So let me write the kinetic energy. T equals, now don't forget that I1 and I2 are A and I3 is C. So T is going to be 1/2 A omega 1 squared plus omega 2 squared plus 1/2 C omega 3 squared. So what I was initially thinking is that many of these terms will cancel, but they don't because of this. Okay, so now we have to live with it. So I'm going to get 1/2 A. If I add omega 1 squared and omega 2 squared, though, these two terms will cancel. So that cancellation is still there. Now here, I have sine squared theta, and then I have sine squared psi plus cosine squared psi. Well, sine squared plus cosine squared is 1. So that's going to give me phi dot squared sine squared theta. I'm going to write the whole thing. Sine squared psi plus cosine squared psi plus these two terms cancel out, so I'll write 0 there. And then I have theta dot squared cosine squared psi plus sine squared psi. There's something satisfying about observing that sine squared plus cosine squared becomes equal to 1, so I don't want to short circuit that satisfaction. And then now, this is a standalone term. And now that's just 1. That's just 1. So I'm going to get 1/2 A phi dot squared. And now the dust has cleared, so I'll expand S for sine. And then I still have this term. So, by the way, if the top were symmetric, if A were equal to C, you'll observe that there's a further simplification, because if A is equal to C, I can take, let me call C A, then I can take these two terms together and I get phi dot squared sine squared theta plus phi dot squared cosine squared theta, which adds up to just phi dot squared. So I'll get an even cuter looking expression, but it's still not trivial. You still have something to do. All right, now for the moment that we have all been waiting for, and that's the moment of writing the Lagrangian. The Lagrangian for the top can be got by subtracting the potential energy from the kinetic energy. Now this top, obviously being a rigid body, has got a mass. And for the sake of simplicity, we're going to assume the gravity acts in the negative z prime direction, as it did in my demonstration. So it makes sense to define some kind of distance here. I'll call the distance between the center of mass and the pivot point, which is the common origin for both the frames S and S prime. I'll call that distance h. So now we have our complete setup for writing the potential energy term. And just for the sake of simplicity, I will take the potential energy of the ground, which is your x prime, y prime plane, to be 0. Okay, so the Lagrangian, which is T minus V, is just that thing minus the potential energy. So I'm just going to copy that down. I'm going to go back to S for sine and C for cosine. I wrote it once so you can see it in full glory, but now I'm going to go back to abbreviation. And remember, because the potential energy is positive, since the top is above the x prime, y prime plane, the contribution, when I subtract, is a negative contribution. Observe that the height, the true height, is mgh cosine theta because of the fact that the location of this above the x prime, y prime plane is that distance. So now we can do some Lagrangian analysis. The first obvious low-hanging fruit here is to ask what are the conserved quantities. So first of all, observe the cyclic coordinates. Cyclic coordinates are coordinates whose derivatives are 0. So the Lagrangian with respect to the phi coordinate is 0. The Lagrangian with respect to the psi coordinate is 0. The Lagrangian with respect to the time coordinate is 0. And that immediately tells us that the corresponding linear momentum or cyclic momentum are conserved. P phi, P psi, and energy conserved. This is another one of the big advantages of the Euler angle formalism. Now, if you have a top just moving around willy-nilly, you would think that there's just one conserved quantity, and that's the angular momentum around the body axis, symmetry axis. Well, the Euler system exposes the true richness of the conserved quantities in the top system. And that's why the Euler coordinate system is to be used to study these things. Now, what I'm going to do next is actually find the corresponding momenta. So the momenta can be found as follows. The phi momentum is found by taking the derivative of the Lagrangian with respect to phi dot. There's a phi dot here, and there's a phi dot there and here. Now, when I take a derivative with respect to phi dot squared, I'm going to get 2 phi dot. That 2 will cancel with the half, and that phi dot is still there. Similarly, here also I'll get a phi dot and a 2. 2 will cancel this, and the phi dot is still there. So I have to pull out a phi dot from both terms. The middle term, the 2 will cancel the 2 here anyway, and the middle term has got phi dot, psi dot. So when I differentiate with respect to phi dot, I have psi dot remaining. And because this is a conserved quantity, I'm going to call this P phi 0. P phi 0 means it keeps the initial value for all time. And that's an interesting statement itself, Because observe, that constant quantity has got all kinds of things in it. It's got a phi angular velocity, a psi angular velocity, these angles theta, which could potentially keep changing as the top moves. So we don't know. Lots of things can be going on, but this particular magic combination always stays the same. Similarly, p psi is del L by del psi dot. And if you differentiate with respect to psi dot, observe that this yields us nothing. All the contributions come from here and here. So I'm going to get C times psi dot cosine theta. Well, I'll do this first, psi dot, and then from here I'll get phi dot cosine theta. And like above, this is also going to be constant for all time. The energy, which in this particular case is just the potential plus kinetic. In general, it's not that simple, but in this case, since the Lagrangian is quadratic in the velocities and does not have any dissipative terms like friction, the energy is just the sum of the potential and kinetic energy. So I'll just write that without any ceremony. Normally, to write the energy, I would first write the Hamiltonian, and then the Hamiltonian will be the sum of the pi qi dots minus the Lagrangian, and it'll all settle down to the same thing. So let me just cut all that work out. Now, when I write phi dot, I'm going to so observe that this thing here, psi dot plus phi dot cosine theta, is just omega 3. Psi dot plus phi dot cosine theta is just omega 3. So since I have deemed that this is constant, it means that this, which is omega 3, must also be constant. So I'm going to write this henceforth as C times omega 3 naught. And so I'll take that understanding back here. Now the square came from squaring that. So I'm simply going back and writing that as C omega 3 naught squared instead of writing all this. And instead of minus, I just put plus mgh cosine theta. And that energy is a constant, so I'll write that as E naught. Now, using the Legendre transformation and Kramer's rule, we can solve for phi dot and psi dot in terms of the canonical momenta, p phi naught and p psi naught. I'm going to leave this as a little exercise for you to do. If you don't like Kramer's rule, you can just solve for a system of linear equations in two unknowns and do it. It's not a big deal. The answer will be phi dot is p phi naught minus p psi naught cosine theta divided by the determinant, which is a sine squared theta. And then psi dot will turn out to be p psi naught divided by c minus p phi naught minus p psi naught cosine theta times cosine theta divided by a sine squared theta. Please pause the video for about 5 minutes to make sure that you get these two. If you want to make it easy, you can use variables like x and y and then substitute back the crazy variables at the end. Okay, so now what I'm going to do is this thing here now, I can write in a slightly different way. This here is a constant because omega 3 naught is a constant. So I can take this constant to the left side and define a new constant energy, E prime. So E prime is E minus 1/2 C omega 3 naught squared. And then I just get that term plus that term. So now what I'm going to do is I'm going to get rid of phi dot altogether. Now, how will I do that? I have phi dot right there. So I can take that phi dot over here and square it and get rid of phi dot. Okay, theta dot will still be there. If you remember what theta dot represents, it represents possible swaying of the top like this. So that motion should not be discounted. It could still happen. So the energy E prime, which is a constant, is going to have that term 1/2 A theta dot squared. And now for phi dot squared, I'm going to substitute this. Big mess. I'm squaring it. I'll also be squaring the denominator. So I'm going to get A squared sine to the power 4 theta, but I have a sine squared theta here already, and I have an A here already. So the A squared will be canceled by the A, and the sine to the 4 theta will be canceled by the sine squared theta. So I'm just going to get that 2 is still there. So 2A sine squared theta plus mgh cosine theta. This object is one big potential energy. It is called the effective potential energy. And in the theory of tops, it's extremely important. Now, we started off thinking that there was only one potential energy, and that is mgh cosine theta. But as the top moves, new sources of potential energy come in, and that's represented by the momentum that you get in these lateral directions, contributing to the potential energy also. So it's like a centrifugal potential energy, if you wish. Remember, in advanced mechanics, centrifugal is no longer verboten. In fact, we encourage it. All right, so now let's plot this effective potential. If you actually take the trouble of plotting this, and I encourage you to do that, putting some constant values like 3 and 5 for this, and put some other constant value there, and just vary theta between 0 and pi, you will find that the effective potential vanishes at theta and pi. Well, that's obvious because at theta equal to 0, the denominator becomes 0, and the same happens at theta equals pi, so that becomes infinity. So you're going to get a interesting shape. It's going to be a U-shaped object. I mean, roughly U-shaped. It's a cubic, so it's not going to be that simple to plot it. But if you take the trouble of plotting it, then that's what you'll see. The interesting thing is, for a fixed value of energy, this cannot go too far away from a certain behavior. So for example, let's fix the energy E prime to be something. This diagram is known as the effective potential diagram. So I'm plotting here V effective as a function of theta, and on the x-axis I'm plotting theta. you observe that all the motion is forced to occur between two turning points, theta 1 and theta 2. So that's reassuring. No matter how crazy you start the stop off, I could have started the stop off in a very crazy way. It'll always nod between two values of theta. Theta is the angle that tells you how far the top is from the inertial z-axis. So it's always going to be nodding between two angles. That nodding can be complicated, and we won't cover that in this video. You can look at my notes for further information on the nodding behavior. The difference between the effective potential and the total energy is, of course, the kinetic energy of the top. So this kinetic energy, 1/2 a theta dot squared, represents the kinetic energy of nodding, not this kinetic energy. That's been subsumed in the potential itself because that is a constant of motion. So it's a very interesting thing. So we'll write a summary. The top motion is bounded between theta 1 and theta 2. Now, the question naturally arises, what is the special value where the top does not change its theta? So that's what we were looking at initially in the demonstration. The theta angle appeared to be fixed. Well, it was slowly decaying and becoming bigger and bigger, but for a given revolution, the theta angle was fixed. So we should try to look for something interesting there. And that also turns out to be the minimum value of the E prime function. And you all know how to get that. You can get that using calculus. Now, what's the significance of the minimum value? If theta is fixed at theta naught, it means the top does not nod anymore. It only precesses. So this is nodding. So I'll write here, if theta 1 equals theta 2 equals theta naught, then no nodding, only precession. And this is what we are after. The gyroscopic precession is what we are after. So that's the last home stretch for this particular video's ambitions, is to study the precessional speed. I'm not getting any more ambitious than that, and I'm not doing the various kinds of nodding that can occur, which any graduate book will cover. See, for example, Goldstein. So I'll write a reference here. Goldstein is now with two other authors, but I'll just write it as Goldstein, second or third edition for the nodding behavior. Okay, now back to the simpler stuff. The simpler stuff is to minimize the energy, find like some interesting conditions that can come, which will inform us about precession. So precession is really important. Many of you may know that Einstein's theory of relativity was predicted that the orbit of Mercury precesses. So the orbit's semi-major axis does not stay in a fixed direction. It keeps changing very slowly, something like 43 seconds of an arc per century. But that precessional test of general relativity proved to be far more exacting test than the slightly showboat verification they had of the eclipse. Well, anyway, to find the minimum theta naught, all you've got to do is take the derivative. So let's do that. Well, the derivative can be got by using the quotient rule. So we are taking the derivative for the theta. So I'm going to get the derivative of sine theta. I'm going to do these two terms separately. The derivative of sine theta here is going to be negative cosine theta because of the sine squared theta being the denominator. The 2 will cancel this half. And so I'll get a sine cubed theta naught. And then this will go along for the ride. Because I'm not differentiating it yet. And then I won't touch the denominator, but I will differentiate the numerator. When I differentiate the numerator, that 2 will cancel the 2 there. So I'm just going to get p phi naught minus p psi naught cosine theta naught. I'm going to put naughts everywhere I see theta because we're going to stay at theta equals theta naught. That's a condition for precession. Divided by the 2 has gone, so I just have a sine squared theta naught. So that's that term. And then I have to differentiate the inside function also. And when I do that, I'm going to get the derivative of cosine, which is negative sine, but there's a negative sign, SIGN, over here. So that those two things cancel out. So I just get p psi naught sine theta naught. And then I have to also differentiate the mgh cosine theta, and that gives me negative mgh sine theta naught equal to 0. So clearly this calls for some simplification. So let's set beta. I'm going to define beta. The colon means the quantity on the left side is defined by whatever is to the right of the equal sign. So p phi naught minus p psi naught cosine theta. Observe that since it's there in both terms, it's easy to write everything in terms of beta. So then we have a quadratic equation. So what I'm going to do is I'm going to take a minus from the entire equation. So that becomes a plus, that becomes a minus, that becomes a plus. So I get cosine theta naught beta squared minus p psi naught. And I'm going to multiply both sides by a sine cube theta naught. So since there's a sine squared theta naught here, I end up getting a sine squared theta naught upstairs. And then that becomes a plus because of the earlier thing I told you of multiplying the whole thing with a minus sign. So that's going to give me mgha. And since I've multiplied by a sine cube theta, there's a sine theta already, so sine 4 theta naught equal to 0. Well, that's a good old quadratic equation. No matter how difficult, complicated it looks, it's nothing more than a quadratic equation. So it's going to have two solutions according to the quadratic formula. What is it? Beta equals negative b, which is this, negative b will be positive this, plus or minus square root of b squared minus 4 this term and that term multiplied together divided by 2 times the coefficient here. So that's the quadratic formula. Now what I'm going to do is I'm going to take out a p psi naught sine squared theta from both sides, from both these terms. So let me do that. Makes it look maybe slightly nicer. When I do that, that becomes a 1, and then I have 4 mgh a. Now there's a sine 4 theta naught in both terms, so that gets rid of the sine 4 theta completely. I wrote the naught in the wrong place. Okay, so that gives us two roots. I'm going to call these two roots beta plus and beta minus. Now, for beta to be a real thing, this quantity had better be bigger than 0. So that's an amazing condition. We are going to demand that this quantity be bigger than 0, which means that p psi naught must be bigger than the numerator. So the condition of reality, I'll call it reality. The reality condition tells us that p psi naught squared must be bigger than or equal to 4 mgh a cosine theta naught. Now, p psi naught is related to the angular velocity. It's just omega 3 naught times the moment of inertia c. That's like the main angular momentum of the body. So we can put that there. So I get a condition for omega naught. So omega 3 naught must be bigger than or equal to taking the square root of everything. So 2 over c root mgh a cosine theta naught. That's absolutely staggering. It tells you that if you're not moving faster than this, you will not precess. Now, many of you are probably aware that the Earth precesses about its axis once every 26,000 years. That's called the Mayan Great Year. That precession will not occur if the Earth were rotating a little bit differently. Our Earth is a geoid, as you may know, so A and C are slightly different, but this condition is absolutely crucial for the Earth to be precessing. The G there is slightly different. It's the tidal acceleration due to the tidal force between the sun and the moon and so on. So it's more complicated. And the H also has a special meaning, but this can be applied to planets. The planets that satisfy this will precess, and the planets that don't satisfy this won't precess. What I'm going to do now is use the equation that we had earlier, which is this one here. I've called that beta because p phi naught minus p psi naught cosine theta naught has been called beta. Well, cosine theta naught, but that's not cosine theta naught there yet. So I'll call it phi dot naught if I put cosine theta naught. And if I put cosine theta naught there and sine squared theta naught there, I'm going to call this phi dot naught. And that becomes a constant precessional velocity. Remember that the precessional velocity is precisely phi dot. So now we have all the ducks in a row, and we can write down our precessional angular velocity. There are two actually. Phi dot naught plus is going to be beta plus over a sine squared theta naught. And that's sometimes called the fast precession. We don't observe fast precession in this setting because it requires great sensitivity to observe it. It's like a flutter. Beta minus over a sine squared theta naught we do observe, and that is the slow precession. Since beta minus is less than beta plus, hence the term fast and slow. Now, I'm going to do a limit so we can actually see something interesting than these monstrous expressions. You know, your beta is this horrible thing there. So let's try to get some intuitive feeling, and that's called the fast stop limit. we already know this fast top limit needs to be satisfied. Otherwise, you could possibly not have precision. So let's assume you're giving the top a really good spin and it's not wobbling and falling down. So this means that omega 30 is larger than others. And if omega 3 naught is larger than the others, it automatically means that P psi naught is also larger. Now, if P psi naught is large, I can simply get rid of this term. Okay, so, well, I don't get rid of it. I use a binomial theorem approximation and write it, the plus sign will give me something, the minus sign will give me something. So I'll write down the result here of that. So the plus will be C omega naught over A cosine theta. And then the minus will be mgh over C omega 3 naught. Now in elementary courses, this is the precessional speed of a gyroscope that you may have found. And this makes sense because I showed you when this gyroscope was moving that as omega 30 decreased due to frictional effects and vibrational effects, the precessional, the gyroscope actually got more and more antsy and more desperate. And so it was precessing like crazy. So that makes sense. So we'll write here as omega 30. It's not supposed to change because it's constant. So we'll say as omega 30 adiabatically goes down, you'll see that phi dot minus goes up. So that explains a very common feature of precessing tops in real life. Well, I hope this gave you a taste of the theory of incredibly complicated theory of tops, and I would not be lying to you if I said that this is just scratching the surface of the subject.